Hello, and welcome to Amazon Web Services Webcast, Amazon RDS for MySQL, Best Practices and Data Migration. Before we begin, I would like to walk the audience through some logistical items. On your screen, you can see a question pod. Please submit your questions for our presenters at any time during this webcast, and we will address them in the live Q&A session at the end of the presentation. Today's webcast is being recorded, and we will send you a follow-up email with the URL to the recording, as well as a link to the presentation deck. And again, welcome to today's webinar, Amazon RDS for MySQL, Best Practices and Data Migration. Our presenter is Manish Delwadi, Senior Product Manager with Amazon Web Services. You have the floor, Manish.
Thanks, Brian. Hi, folks. Thanks for taking the time to attend this webinar. My name is Manish. Today I want to spend a little bit of time talking about Amazon RDS for MySQL and best practices when using Amazon RDS for MySQL. So I'm going to spend a little bit of time just at the beginning of this webinar just to introduce you guys to those folks that may not be familiar with RDS, just to talk about what it is and what it does. And then I'll spend the majority of the time talking about best practices in terms of high availability, disaster recovery, high performance, and finally data migration. So let's jump into this. What is RDS? Amazon RDS is a web service that makes it easy to set up, operate, and scale a relational database in the cloud. And it's compatible with your existing apps. So today we support 4 different engines, MySQL and Postgres for open source engines, and then Microsoft SQL Server and Oracle. With those engines, we make it easy to set up, operate, and scale them. And here's a couple of ways we can do that. One is ease of deployment. So you can go to our AWS Management Console, or you can go to our CLIs or our APIs. And with a call of an API or a push of a button, you can deploy any one of these 4 databases in 5 to 10 minutes. So basically, you push a button, the database is provisioned, created, the volumes are set up for you, and then you basically can start connecting to it and send SQL at that database. We also do patching for you. So if there's a security vulnerability that comes up, or there's a new version of MySQL that's up, we can auto patch your instances within your weekly maintenance window. We also do automated backups. So here on a nightly basis, RDS will automatically take a snapshot of your database, and then during the day, whenever any changes are happening to your database, we'll keep track of those updates to your database and store those in S3. So at any point, if you ever want to recover your database to some point in time, you can say, RDS, give me a new database that looks like my old database at, say, 25 minutes ago down to a certain second. And RDS will go ahead and bring up that database for you. And you can set that backup retention window so that the amount of time you can go back in time to 35 days today. We also do push button scalability. So if you want to increase your CPU or memory, you can just with a push of a button go ahead and increase your database instance from T1 Micro, which has like 1 CPU and 600 megabytes of RAM, all the way up to our CR1 8 extra large, which has 32 vCPUs and 244 gigabytes of RAM, which is a pretty big instance. There's also a feature with failure detection and automatic recovery. So RDS will monitor your databases, and if something ever happens to your database, we'll detect that and go ahead and replace that database for you and bring you back up to normal operation, all happening without you having to interact or take action on your end. And then in terms of alerting and monitoring, RDS has 14 different monitoring metrics that you can watch. You can set alerts on these. So if you want to know if your CPU is going above 75 to 80%, you can set an alarm and be warned that that's happening. You can also set up SNS messages where if a database failure occurs or your backup didn't take place properly during the right time, you can get an email or an SMS message letting you know that those things happened. These are just some of the things that RDS offers that makes it easy to set up, operate, and scale databases in the AWS cloud. But let's spend a little bit more time on the best practices because that's what this webinar is about. So let's start with high availability. Our flagship high availability option with RDS is something that we call multi-AZ deployments. And what you can think of as a multi-AZ deployment is essentially RDS will maintain a hot synchronous backup of your database in a different AZ, and you can we'll fail over to that database if something happens through your primary database. So let's talk about this in a little more detail here with these diagrams that we have on the screen. So here we have one AZ1. Your application's there, and there's an RDS primary database sitting there. If you decide to convert that to a multi-AZ deployment, this you could do through our APIs or through the management console with a push of a button. RDS will set up a secondary database in a separate AZ. And if you're not familiar with Amazon Web Services availability zones, AZs are designed to not have correlated failures. So they're going to be on different floodplains, different power, but they will have high bandwidth, low latency connectivity between them. So once we set up your secondary database in that second AZ, we'll set up synchronous replication between the primary and secondary for you. And with synchronous replication, what's really happening is say your application says, I want to insert a record into a table. Well, the primary RDS database will make sure that record gets inserted on the secondary database as well before it acknowledges durability to your application. So there's a trade-off there. You're getting higher durability, and you're also getting the potential for higher availability. But you are you're adding a second write to your insert, which means your latency on your request will go up. The other thing that we recommend is if you do use multi-AZ deployments, we recommend that you design your application tier to have your application, say your Apache web server, or Nginx, or whatever it is, in multiple AZs, such that if AZ1 went down in this scenario, you're able to restore to AZ2 without having to create new EC2 instances and set up web servers and connect them to your database. It just lets you get up faster. So let's play out a scenario here. Let's say your primary database fails, and RDS is actively monitoring your primary database and your secondaries, and it sees that the primary database has gone down. Well, what it's going to do is it's going to promote your secondary database to become the new primary. It's then going to update your CNAMEs via DNS. So your application is going to be using a DNS record to connect to these to your RDS database. That CNAME update will occur, and then your applications will start pointing to your primary. So what's going to happen is when that update happens, there is a period of time when your database will see errors because it's essentially trying to still connect to the old primary, and now you're updating the DNS to point to the new primary. One of the new features that we've released is it takes less than 2 minutes for that failure to occur now. And then, so in this scenario, as the failover happens, your application has an interruption of about 2 minutes, and then you're writing to your primary, but your secondary is still down. And so if you had another failure happen in AZ2, well, now you've actually lost both of your databases and you have an outage. So what RDS will do is it'll reestablish that secondary for you and send the data to your secondary and synchronize. So you're back into this multi-AZ state. We support this feature for MySQL, Postgres, and Oracle for over the past 2 years. However, earlier this week, we announced a new engine for support. So we added support for SQL Server. So now you can do multi-AZ with SQL Server Standard Edition and Enterprise Edition, which is pretty exciting for SQL Server customers. Another way to achieve high availability is using MySQL read replicas. And so here in this scenario, we have an application, and it's writing to a multi-AZ deployment and writing to your primary. And so you have a synchronous secondary. What you can do is create read replicas via asynchronous replication. And these replicas are MySQL read replicas, and they essentially work using MySQL bin log replication. It's a native replication technology in MySQL. And since it's asynchronous, though, when a write happens on the primary, there's no guarantee that it's going to happen on the read replica. So what can happen is your read replicas can lag behind your primary by seconds, milliseconds, depending on the change rate that you're sending to your primary database. But what these read replicas let you do is segment the type of traffic that your application is using. So in this scenario, imagine if you had a e-commerce site and you have two types of workloads. You have a shopping cart, which requires pricing and quantities, and they get updated. And so in this case, you need to be able to write to your shopping cart, and you need to have consistent reads because you need to have the latest price and the latest quantity that's in the shopping cart. But you could also have your product catalog, which is just pictures of your products and maybe descriptions of your products. And those don't necessarily need to be completely up to date. So what you can do is you can send your product catalog, those things that you only need eventually consistent reads, to your read replica, and you can send your shopping cart or things that need to write to the database or have consistent reads to your primary database. And you can even add more read replicas to support your eventually consistent reads as well. But what's interesting about this is since we've segmented the traffic, if a failure happens on your primary, RDS will detect that failure, just like we talked about in the previous slide with multi-AZ. It'll promote your secondary to become the new primary and reestablish replication with your read replicas. But in the state, what's interesting is the only part of your application that's been impacted is the part that requires writes and consistent reads. Your product catalog was not affected here, whereas your shopping cart was. So that's a way to isolate parts of your application so that you're more available for certain pieces of traffic. And then RDS will do the DNS update, the 2-minute update takes place, and now you start taking writes and consistent reads from your primary. You can use this approach to upgrade your instances as well. So say, for example, your shopping cart application suddenly is being overwhelmed with lots of updates, and you need to upgrade to a larger instance. Well, again, you can update your primary instance to, say, go from an M1 large to an M2 4 extra large without impacting the browsability of your website in terms of your product catalog. You can do the same thing with read replicas. You can take any one of these read replicas and upgrade it, and you can add more read replicas. So in this case, you can actually increase your eventual consistent reads without having to take downtime on that traffic that's happening. So this is a great way to kind of segment your application's traffic and allow certain parts of your application to experience lower availability, but provide higher availability for other parts of your applications. So we recommend when you're building your applications to think about how can you split up your workload such that the things that need to be consistent reads or writes are sent to your multi-AZ instances. Things that don't need to be eventually consistent, you can achieve higher read availability with eventually consistent reads by using MySQL read replicas. Another impact to availability is when you want to change your schema, or say you want to build a new index on your database, or you want to add new columns to a table within your database. Those things can take a lot of time. Depending on the size of your table, an index rebuild can take hours. And if you try to do that on your primary database, you're looking at hours of outage. So one way to get around this is to actually use read replicas. And so in this scenario, again, so we have 2 read replicas and we have a multi-AZ instance that's a primary with synchronous replication to a secondary. What you can do is convert one of those read replicas to a read-write replica. And the way to do that is using our DB parameter groups. There's a parameter in there called read_only. You can change that setting and essentially convert the read replica to be writable as well. Once you do that, the thing to remember here is replication is still happening. So the primary is still taking updates. So there's no outage to your application tier here. All the changes from your primary are still asynchronously being replicated to that replica. So the changes that you make to that replica, you need to be very careful so that they're not breaking. So if you make certain changes that cause replication conflicts, the replication will actually break, and then the replica is no longer replicating with your primary. So as long as you take care of that, you can create the index, have that index rebuild without having any impact on availability of your application. You can go ahead and create read replicas off of that read-write replica. And when you're ready, you can let that the read-write replica, basically catch up all the changes, convert it to a new primary. And now effectively what you've done is you've gone to a new schema while minimizing the availability impact of actually doing that. And then you can turn on multi-AZ to bring it back to a production status for your applications. Another application for this is we recently announced the ability to upgrade from MySQL 5.5 to MySQL 5.6 via read replicas. So using the same process, what you can do is you have a primary instance that's MySQL 5.5. You can create a read replica that is MySQL 5.6, and then you can promote that read replica to become the primary when you feel like it. And now you've effectively been able to move from 5.5 to 5.6, again, in a with a very low impact on your availability. And there's a few things to think about when working with MySQL read replicas. The first thing is MySQL replication is single-threaded. So the way to think about it is the actual database, your primary database is not single threaded. You can have many, many users, many, many threads with high concurrency updating your database on your primary or your master database. But all of those changes have to be sent to the read replicas, and those get applied in a single threaded way, which depending on your change rate, you can imagine if you only have one thread, your read replicas may lag over time. And so one of the things to pay attention here is we have a CloudWatch metric called replication lag. You can set up alarms on that to see how far behind your replicas are lagging from your master instance. It's a sign that things may not be working quite right for you. Another thing is if you're using MySQL 5.1 and 5.5 or 5.5, um, the the ability for a replication to be reestablished after a primary or master crashes and crash recovery is done on that master is not completely guaranteed. And the reason it's a little subtle here, but the reason that that's happening is basically with 5.5 and 5.6, the default for the sync bin log function is set to 0. And what that means is MySQL is basically saying, hey, anytime an update happens to my database, go ahead and create the bin logs, but only flush those bin logs, which is the bin logs are essentially the transactions that get replayed on the replica. Only flush those bin logs to disk when it makes sense. So it relies on the operating system to optimize the I/O workload that's sent to the disks. But if a crash happens before some of the bin logs have been flushed to disk, well, then you end up in a state where your master instance has some records or some updates and your replicas don't have them, but you also don't have the bin logs to get the replica up to date. At this point, what happens with RDS is we will actually stop replication and will require user intervention on your end. You have two options in that state. One is you can go ahead and just delete those read replicas, create new read replicas. That's probably the safest approach to make sure that you don't have any missing data. But if you understand that there's no data loss, you're not worried about the bin logs that may have been lost. We do offer a stored procedure called RDS underscore next underscore master underscore log, which allows you to essentially go to the next available bin log and start replication from there. Again, just be very careful because there is potential for data loss if you use this command. However, with 5.6, which is the version that we recommend using with RDS, it's also our default version now. We introduced crash save slaves. And so here we do enable sync bin log to 1 by default. And what that means is anytime there's a commit that happens on your database, a flush of that bin log is sent to disk. So what that means is that even if a crash happens, you're guaranteed to have the bin logs in place. There is a performance implication here because now the operating system's not able to optimize the I/O flush that happens when you have your bin logs, which means every time there's a commit, you have to flush the disk. So that does impact your I/O performance. However, we highly recommend if you are using read replicas, you maintain the sync bin log option set to 1 because it basically guarantees that even during like a multi-AZ failover, we're able to reestablish your read replicas and start replication. Okay, so let's switch topics and talk about disaster recovery. So you may be thinking, well, I've got read replicas and I've got multi-AZ. Why do I need anything else? Well, when you think about read replicas and you think about multi-AZ, well, those are all based on replication technology. So imagine a scenario where you have a power user that accidentally drops a table, or you have a logical corruption that ends up corrupting an entire column in your database. These technologies, multi-AZ and read replicas, will just propagate that logical error to all of your databases. And so effectively, you'll have a corrupt database in 5 different places if you have 5 replicas. So to protect against that, RDS offers a continuous and incremental backup and restore feature that we call point-in-time restore. And the way that works is anytime there's a change to your database, we send those logs to Amazon S3. And the reason we send those logs to Amazon S3 is Amazon S3 is designed for 11 nines of durability, which means it's really unlikely for you to lose data once it's in Amazon S3. So it's kind of like your last best hope if everything else has failed and you need to pull from somewhere. Amazon S3 is that fail-safe for you. So we keep track of the logs, but also on a nightly basis, we take a snapshot of your database. And you can basically keep up to 35 days of snapshots. You can set that via our API or our management console. The setting is a backup retention window, and you can set it from 1 to 35 days. Um, So if you want to store data past 35 days, we also offer a DB user snapshot feature. So if you want to keep stuff outside of that 35-day window, you can take a snapshot. That will also be stored in Amazon S3. And that will not get removed or deleted by RDS. It will stay there indefinitely until you choose to delete it. And so some of the things that I see with customers is I'll see customers set their backup window to 7 days. So they get a week of point in time restore. So they can restore to any point in time down to the second within a week. And then they keep a weekly backup for a month. And then they keep monthly backups for maybe a year or 2 years after that. And so that way they have different granularity of backups if things ever go wrong for them. So let's go back to the example of where like a customer dropped a table and you're trying to restore that table. What you can do is you can say, RDS, give me the database at a point in time where I think the dropped table still existed. And what RDS will do, it'll take the latest snapshot that you have, and then it'll reapply the logs to get you to that exact moment in time that you requested down to the second, and give you a test database that you can start looking at. So at that point, you can look at the database. You can see if that table is there. If it is, you can merge it back into your prod database. If it's not, you can pick a different time, do the restore, and do the same thing until you can find the table that was dropped. Another disaster recovery feature that we provide is cross-region functionality, and we support two features today. We have cross-region snapshots, and we have cross-region read replicas. The way cross-region snapshots are pretty straightforward. You have two regions, and you have a database in region one. You can take a snapshot of that database and store it in Amazon S3 in that region. You can then request that that snapshot be sent to Amazon S3. And what I see customers do here is a lot of customers actually have tools set up that use our command lines or our APIs and actually schedule on a nightly basis, take a snapshot and move it to region 2. So every day you'll have a backup of your database in a different region just in case something bad happens in the region where you're actively running your database. And if something ever did happen in region 1, you can restore your database in region 2 and start taking writes from that perspective. The other feature we have for disaster recovery in terms of cross-region is read replicas. And this is one of my favorite features with RDS because I think it's very powerful. What you can do here in this scenario is you have a read replica with, I'm sorry, you have your production database and you have a read replica attached to it in region 1. You can just with just one API call or a push a button, you can say, hey RDS, create me a read replica in another region in some other AZ. And then you can create read replicas off of that. And so there's a bunch of different use cases that can apply here. For the disaster recovery scenario, say some natural calamity happens in region 1. Well, you can just promote your cross-region read replica to become a new production instance, and now you can take read-write traffic on that instance. Another thing you can do, and this is something that I've seen customers do, is during a storm like Katrina or as a large hurricane coming on the East Coast, you can use this approach to actually proactively migrate away from a region that may be experiencing a storm or will be experiencing a storm in the next couple weeks. So you can essentially create a replica. Say you're in Virginia, you can create a replica in Portland, Oregon, and move your data over there and then fail over to that. And now you're essentially moved away from a region that has some higher risk than you're willing to tolerate with your application. And then the third use case here is just in terms of read latency. So if you have a global application or you have customers on the East Coast and West Coast of the United States, you can basically have customers, you can have a read replica on the West Coast and your primary database on the East Coast. And so your West Coast customers will get low latency reads since they're being served out of a West Coast database. So those are sort of three things you can use with the cross-region read replicas. Again, something I think is very powerful when operating databases. Okay, so let's switch topics again, and we'll talk about best practices for high performance with Amazon RDS for MySQL. Our flagship uh, performance feature is something that we call provisioned IOPS. Sorry, it looks like we're having some trouble with the slides here. The slides aren't showing the
Please stand by. We're correcting a small problem. Thank you.
Testing 1, 2, 3. Is that better? All right, we're gonna do this one more shot here. Sorry, guys. I really do apologize for just having some trouble with the presentation software here. All right, I'm gonna go through this again. So let's get back to high performance. Our flagship product in terms of performance with Amazon RDS is provisioned IOPS. And so here's a benchmark. On the y-axis, you'll see transactions per second, and there's 3 different workloads here. The blue workload is RDS MySQL using magnetic or regular EBS volumes. The yellow or orange line is RDS MySQL using PIOPS and 1,000 PIOPS. And the top line, the black line, is RDS MySQL, again, using PIOPS, but this time with 30,000 IOPS. And I want to call out 2 things here. One is on the blue line, you can see a lot of volatility in terms of the performance, transactions per second that you're getting over time. It can range from 5,000 transactions per second all the way up to 10,000 transactions per second. And what you see with the 2 PIOPS workloads is a much more consistent experience, hovering around 10,000 and around 20,000. The other thing to notice here is as you add more PIOPS, you're able to increase your transactions per second. But let's take a deeper look at what's actually happening at each request, the latency involved to actually return a success on the partial read workload here that we're testing. So this graph, what it's showing you is the latency split for all the requests that happened during the benchmark that we ran. And so what you're seeing here is a 3 to 20 millisecond bucket, a 20 to 500 millisecond bucket, and a greater than 500 millisecond bucket. Obviously, these numbers don't add up to 100% because there's a less than 3 millisecond bucket, which is where most requests are actually served from, but we exclude that to make the graph a little more readable here. But what you'll notice here is at the high end, so these are the really bad outliers with greater than 500 milliseconds. You won't see those outliers with PIOPS, but you see them with standard storage, standard volumes. And those outliers can have a real impact on your database because effectively every now and then when your application tier asks for something from your database, it has to wait more than 500 milliseconds to actually return it. So it can have a really bad impact on workloads that require consistent high performance. And the thing about the benchmark itself is that we're pushing the transactions per second to max out the IOPS and storage that were available. But let's imagine a scenario where we provision the same amount of IOPS, same amount of standard storage, but we set our target transactions per second at 5,000 instead of 10,000. Here, something really interesting happens. What you'll see is, number one, there's no performance outliers with provisioned IOPS. So the latency on every request that happens in that benchmark is going to be less than 20 milliseconds. And there's nothing that's going to happen at the greater than 500 millisecond aspect. But the other thing to realize here is if you're using magnetic volumes, you're still even with lower transactions per second at 5,000, you're still getting those performance outliers at greater than 500 milliseconds. So the takeaway here is if you're using magnetic storage, regardless of what you're doing with the storage itself, you're going to get a high variance in terms of the latency profile of the requests you send to the volume. Whereas with PIOps, you're going to get very predictable, very low latency for the requests that come on. So for production workloads that are latency dependent, we highly recommend using provisioned IOPS here. But so that's about the latency. But what about the actual, increasing your transactions per second? So here, same workload for the blue, orange, and black line here, but we added one more where we added a new workload that's RDS MySQL running 10,000 PIOPS. And so what you'll see here is the RDS MySQL with 1,000 IOPS is giving about 10,000 transactions per second. And the new workload we added in pink, which is 10,000 IOPS per second, is getting about 40,000 transactions per second. So what we did is we increased the IOPS by 10x, but we're only seeing the transactions per second increase by maybe around a little less than 4x. So what's going on here? Well, we can use CloudWatch to understand this a little better. So in this graph, you'll see CPU utilization and read IOPS. And so the CPU utilization is in orange, and you'll see that we're not really hammering the CPU that bad. We're still only at 80%, so definitely the CPU is not the bottleneck here, and there's definitely room for the CPU to go up. But our read IOPS are basically bottlenecked at about 6,000 per second. So what's going on? Well, if we look at some of the other CloudWatch metrics, the one that's really interesting here is our read throughput in terms of bytes per second. And what's happening here is the network bandwidth associated with the instance is acting as the bottleneck now. So if we were able to have more bandwidth associated with the instance, we'd be able to achieve more IOPS and thus more transactions per second. But in this case, we're hitting the 100 million bytes per second here, which is the limit on that instance. And as a result, the transactions per second as well as the IOPS per second are being limited. And I'll talk about this in a little more detail in the following slide. So there's going to be bottlenecks that happen with the database. And so one of the bottlenecks could be your CPU bound or your memory bound. And you can use database instance classes to help grow out and unlock those bottlenecks. And today we support T1 micro all the way up to CR1 8 extra large. Talked really briefly about that earlier, but that goes from 1 ECU all the way up to 88 ECUs and 600 megabytes of RAM all the way up to 244 gigabytes of RAM, which is a pretty big database instance. You can also, in the benchmarks we showed, you can see as you increase your IOPS, you're able to achieve more performance. So you can go from 1,000 IOPS all the way up to 30,000 IOPS. And I mentioned these ratios of 3 to 1 all the way to 10 to 1. Essentially what that means is you can, if you have a really hot workload, you can allocate 10 IOPS to every gigabyte you've provisioned in terms of storage. And if you have a less of a hot workload, you can go down all the way down to 3 IOPS to 1 gigabyte of storage. So depending on the workload you have, you can tune that ratio to match what your needs are. But even if you unlock the CPU and you add all the IOPS in the world, your throughput is controlled by the amount of bandwidth associated with the instance that you're running on. And so one of the ways to help alleviate that is we do offer special instances that are EBS optimized, which means there's a dedicated portion of bandwidth that is always there for the database or RDS to actually write out I/O to disk. And so there's different instances. They can range from 500 megabits to 1 gigabit for some of our M1 and M2 instances, and our CR1 8 extra large has 10 gigabits. What's interesting is if you don't use EBS optimized, so you're using standard or regular storage and non-optimized, what that means is the bandwidth is shared between the data that needs to get written to EBS and the data that you're inserting into the database. And as a result, that can result in the database essentially having contention for the bandwidth available for that database. So here's a quick benchmark here that kind of highlights what's happening in terms of bandwidth available for EBS and writing out to EBS. So here's an M1 large, and we have 52 megabytes per second. And here's an M1 extra large, which has more bandwidth. And you can see that we're pegging the CPU. So we were able to achieve more megabytes per second because it has more EBS optimized bandwidth. But now let's go to the M2 4X large. This is where something interesting happens. The CPU isn't as utilized because the M2 4X large has more CPU, but the megabytes per second remain the same. And the reason that's happening is because the database or the instances have the same network bandwidth associated with it. And then let's talk about the CR1 8 extra large. Here's something interesting. You don't see much of a gain, at least with this benchmark, in terms of the transactions per second. And you also aren't seeing any megabytes per second being sent out as well. So this is a little interesting because the benchmark we're using, it's a 130 gigabyte data set. The CR1 8 extra large has 244 gigabytes of RAM. As a result, the entire data set lives in memory, and so there's no reason to actually write out to EBS most of the time. But the last thing I'll talk about with scaling for performance is you can use read replicas to scale performance as well. So imagine you have an application with 95% read and 5% write, and they're all being sent to your primary CR1 8 extra large, and you're getting the 47,000 transactions per second. Well, imagine if we took that e-commerce example where we have eventually consistent writes for the product catalog and then a shopping cart that requires writes and consistent reads. And so in that case, if we added 3 read replicas for the eventually consistent stuff and and the CR1 instance for the shopping cart, we're able to more than double the bandwidth available to more than double the transactions per second delivered for this benchmark. So this is a great way to scale your transactions per second using read replicas. So there's some things to consider when using provisioned IOPS. The first thing is make sure if you're going to use provisioned IOPS, use EBS optimized. So there's different instances with different bandwidth associated with it. The thing to remember here is to understand what we mean by that bandwidth or the channel bandwidth. And when we define, say, for an M1 extra large, we say 1,000 megabits per second. That's a full duplex number. So what that means is that you get 1,000 megabits per second for reads and 1,000 megabits per second for writes. So 1,000 megabits per second translates to maybe what we estimate to be about 6,250 16 kilobyte IOPS, which is the 16 kilobits is the size of IOPS that MySQL writes out in terms of pages. If you do reads and writes, then the max realizable IOPS that you can get with M2 4 extra large with MySQL is 12.5K 16 kilobyte IOPS. And our benchmarks show that you can achieve about 20K with CR1 8 extra large. There are benefits to going past those max realizable IOPS. As you increase your IOPS, you're able to reduce the latency of your applications. And so if you set it to 12.5 and you're not getting the latency you like, you can try and bump up the IOPS and see how that impacts the performance of latency on your workload. And if you're not getting the IOPS that you expect, you can, again, make sure that you're running EBS optimized, provision IOPS optimized instances. Automated backups, snapshots, and scale storage also eat up a lot of IOPS. So if any one of those are happening during the time that you're running your benchmarks, your applications, they can have a real impact on the IOPS that your application tier can consume. Also review the QDEP. This is also a CloudWatch metric. What we recommend as a best practice is for every 1,000 IOPS allocated or provisioned, you should maintain a QDEP of 1. So if you have a QDEP less than 1 with 1,000 IOPS, that means you're not utilizing all the IOPS that are there. If you have a QDEP greater than 2, that means you would benefit from adding more IOPS or provisioning more IOPS to your database. And then there's also database contention, locking, deadlocks. So at the application level, make sure that the concurrency that you're applying to the database isn't resulting in poor performance in terms of deadlocks and locking, which can also cripple the throughput of your database. Some other best practices here are around, we highly recommend using InnoDB instead of MyISM. InnoDB is the default storage engine for MySQL 5.5 and 5.6. MyISM does not provide true ACID properties, and in addition, doesn't work well with point-in-time restore or read replicas. We also recommend using CloudWatch alarms. There's 14 different CloudWatch alarms. These are really powerful to keep track of what's happening to your database. We also provide email notifications where you can do failovers. And when a failover occurs or replication breaks on your read replicas, you can be warned. So this is a great way to start up your instance, let it run, and then know that you'll be warned or notified when something is happening to your instance that you need to take action on. Last thing I'll mention here, since we're starting to run out of time and I want to leave some time for question and answer, is the number of tables available. MySQL Crash Recovery will do crash recovery on each table. So depending on the number of tables you have, it can take a really long time for crash recovery to complete. So with standard volumes, so EBS standard volumes, we recommend no more than 1,000 tables. And with EBS PIOps, we recommend no more than 10,000 tables. So Brian, I'd like to open this up to question and answer. Thanks.
Thank you so much, Manish, for an informative presentation. And thanks to the audience for submitting great questions, as well as thank you very much for your patience during our technical difficulties. As Manish reviews the Q&A questions, let me launch today's poll. Here's the first question. What is the topic you want to learn about next? Please take a moment to vote. The next question is, how effective was the presenter in communicating the material? Please take a moment to vote. The final question is, how satisfied are you with today's webinar? Please take a moment to vote. Thank you very much. Your feedback is greatly appreciated and will help us improve our webinar platform and program. And we'll now start the Q&A. Back to you, Manish.
Thanks, Brian. So sorry about those delays with getting the slides working, guys. So I want to just tackle some of these questions that are coming through, and I'll try and tackle as many as I can. So there's a bunch of questions around multi-AZ here. One of the questions that comes in here is the CNAME update, will that be done automatically? So yes, the way multi-AZ works is we will automatically detect that there's a failure on your primary instance, and we will update the CNAME for you. That time to do that update is about 2 minutes. And so you don't need to do anything. The only thing that we ask that you do to basically make your application tier resilient to those 2 minutes of where your database will actually be, when you're connecting to the database, you'll be seeing some errors. So putting in the retry logic with exponential backoff, things like that, are going to be super critical to make sure that you're tolerant of that actual CNAME update and failover. Another question here is the multi-AZ deployment using built-in replication functionality provided by the database? So no, so we use MySQL binlog replication, which is the native MySQL replication for read replicas, but we use our own technology, which is a physical synchronous replication technology behind the scenes to ensure that the data on your primary is always replicated to your secondary. So another question here, what happens during an upgrade on a primary? How long does it take? And is there any chance to lose an insert in a DB? So it depends on if you're running multi-AZ or single AZ. So if you're running multi-AZ, the way that works is we'll go ahead and update your secondary for you first. So your primary remains up. You continue to take reads and writes on your primary. We'll go ahead and essentially what we call scale compute your secondary for you to the larger instance or the smaller instance. And then we'll execute a failover. So that's when you'll see that 2-minute CNAME update to point you to the secondary. And then once that's happened, we'll go ahead and upgrade your original primary and basically scale compute that to the smaller or larger instance that's available. So there's a 2-minute outage there. And there is no chance of losing data. With multi-AZ, we guarantee that synchronous replication. So if there is ever a failover, we guarantee that there is no data loss during that failover. So there's a bunch of questions about some new features that are coming to RDS, or when will new features come to RDS, like when will RDS support R3 instances? Can I have access to the actual operating system? So this isn't, unfortunately, this isn't the forum where I can talk freely about some of these things, but what I do is we do take all of these questions, we aggregate them, and we use them to guide our roadmap moving forward. So I can't share any plans right now, but please let us know if there's specific things you want to see with RDS. We take that feedback incredibly seriously. It's probably my main job is to understand what you guys want and figure out how to get it to you guys. So please just make sure that you send in this chat window, send everything that you want, and I'll make sure to review them and prioritize. So this is a great question. Is it possible to replicate from an external database to RDS? Part of this presentation was to talk about a little bit of that, so I'll spend a little bit of time just to talk about it, just so you guys are aware of it. Absolutely, it's possible. What RDS allows is binlog or MySQL replication from your on-premise database to your RDS instance. So what you can do is this is a great way to go ahead and dip your toes and try out RDS MySQL for some part of your workload, and it's also a great way to actually migrate to RDS MySQL. And so I'll just cover the high-level process here. The way it works is you can think of it as a two-step process. First, you have to establish a baseline of your database. So you get a consistent snapshot of your database that's on premise, and then you migrate that to RDS. And then while that migration is happening, depending on how big your database is, that could take a couple hours or days if you have terabytes of data. During that time, your on-premise primary instance continues to remain up and it can take traffic. So you're not going to see any outage in terms of reads or writes from your application tier. Once the baseline copy has been copied into RDS, you can now set up replication between your on-premise database and your RDS database, your new RDS database that has that baseline. And from there, you just let replication catch up. Then you'll take a small brief outage where you turn off your application so that's no longer pointing to your on-premise. You let replication completely filter through. Then you point your application to the RDS database that you created, and off you go. So you basically did a near zero downtime migration. There are some slides with some, at the end of this presentation that's attached, there are some slides where you can take a look. They're pretty detailed examples. There's actual CLI commands, there's some diagrams, and as well as some reference material where you can actually take a look and see how exactly to do this. Well, here's another question. Is there any guidance around recovery of individual DB schemas? So within a single DB instance, if you have a database specifically. So unfortunately, the way RDS works today is our point-in-time restore functionality will restore the entire database, as well as our snapshot functionality. It's going to be the entire database. What you can do in the example that I talked about in this presentation is what you can do is if you do lose a specific table or you want to get a specific information about some specific part of your database schema, you can do a restore to that point in time, and then you can merge those tables that you want from your backup that you just created, merge those tables into the production instance that you have. Um, Another one here is, can read replicas act as failovers? So definitely you can fail over to your read replicas. It is a manual process though, because one of the things that we promise is that we won't fail over your database if we think there's potential data loss. And so with read replicas, there's a potential for replication lag to exist since it's using asynchronous replication. Whereas with our multi-AZ functionality, we guarantee that it's synchronous. So with multi-AZ, for sure, we will automate the failover because we can guarantee that there won't be any data loss. With read replicas, you can do so, but you'll have to go in. You'll have to go in and say, okay, I've detected a problem. I want to promote my read replica to master. And the reason we do that is we want to make sure that as a customer, you're making a decision to basically say, okay, I understand that there is some potential for data loss. You understand your data better than we can. So as a result, we want to make sure that you guys take that explicit action and decision on your end. We don't want to do that automatically for you. And I do see the +1 from MariaDB, and I'll echo that. So here's a question about encryption on backups, as well as encryption on the database itself. Um, so today RDS does not support encryption of data at rest. So on your volumes within EBS or within your volumes or your backups that are stored in S3, neither are encrypted. We do support transparent data encryption for SQL Server and Oracle. And in that scenario, your database is encrypted at rest as well as your backups. So both would be encrypted. But currently, MySQL does not support that. But again, something that I see here and I know is very important. Now the question here, someone trying to upgrade from MySQL 5.5 to 5.6, and they're getting an error message that says, cannot upgrade MySQL from 5.5.27 to MySQL 5.6.17. So the issue here is right now we're not allowing direct major version upgrade from MySQL 5.5 to MySQL 5.6.17, but you can go from 5.5.27 to MySQL 5.6.13 and then do a minor version upgrade to 17. The reason we're doing that is because we just released MySQL 5.6.17 yesterday, actually I think last night. And so we're just making sure that it's working properly before we have it become the default for customers automatically. So that will be coming soon. Here's a question on our replication. So this question is all replication query based or is it row based replication? Is row based replication offered as well? So Here, I assume you're talking about bin log replication, so using MySQL native replication. Multi-AZ replication is done on a different level. It's not using bin log replication, so it's physical, so it doesn't rely on queries or rows or anything like that. Today, RDS supports mixed mode replication. And so essentially what that means is MySQL will intelligently decide when it makes sense to replicate via statements and when it makes sense to replicate by rows. So depending on if you have like a sysdate or something in your query, it'll decide to use row-based. If you're doing something like a big insert, it may do query-based. And so MySQL will optimize around that. I am curious, just if people on the line are interested in this, if you do respond in the chat, are you guys interested in seeing row-based replication, statement-based replication, being able to control that more explicitly? I'd love to see if there's any feedback there in terms of yes or no, and maybe a quick why you care. So there's a question about cost analysis here. So what we recommend here is we do have our website, Amazon RDS, and there's a pricing section under there that highlights all the different prices as well as our reserved instance pricing. I would point you guys there for specific cost questions in terms of price. Um, what I do recommend in terms of doing like the performance to price type of analysis is benchmarks can give you a little bit of a view, but nothing really replaces what your workload does. So generally, when I work with customers, I like to have them run their benchmarks against RDS as well as the alternatives that they're looking at, and then do the price performance comparison there. I think it just gives a much better comparison. This is actually an interesting question. Backups were mentioned as a significant source of IOPS. If we're not using PIOPS, are those billable or do they fall outside of that rate? So PIOPS and standard volumes are priced differently. With PIOPS, we price at 10 cents IOP and 12.5 cents a gigabyte month. Um, and with standard storage, we charge I forget the exact price on storage itself, but I think it's 5 cents or 10. Sorry, it's 10 cents a gigabyte. And then we do charge per million IO. However, if you are using standard storage and you are taking a backup, it does use IOs, but it's per million IOs. So the cost associated with those IOPS is very, very small. And so generally you won't see too much of an impact on your bill there. However, if you are using IOPS, you are paying for those IOPS, and those can be a significant portion of your bill. I'm sorry, if you're using PIOPS, they can be a significant portion of your bill, and as a result, those can actually take a large percentage of your bill. So I think we're running out of time here, and so there's a few more questions that I'm not going to be able to get to. What I will say is that we will do another webinar to talk about data migration. I see a lot of people asking about that, so I do apologize that we didn't get to that. We did have some technical difficulties, which is what caused some of that. So I do apologize, but definitely we will make sure that we make the time to do a specific webinar on data migration as well. Thanks, guys.
I'd like to extend a special thanks not only to Manish, but also to all of our attendees. Within the next few days, you'll receive an email with links to the webinar recording and more information. If you have any comments on our previous and upcoming webinars or suggestions on the topics that you would like AWS to cover in its future webinars, please email aws-webcasts@amazon.com. That email address again is aws-webcasts@amazon.com. Your feedback helps us improve our webinar programming. Again, thank you for taking the time to join us today. Please enjoy the rest of your day.